So they're asking two questions. How fast is the car traveling at the bottom of the ramp, and what is the acceleration of the car when it's on the ramp? So hear the word acceleration. That seems to me to suggest force questions, because force questions can only do two things. They can tell us the size of a force or the size of an acceleration. So and the reason I'm saying that is because as your tests become more complex, you're not going to know, it's not going to say this is a force problem, this is an energy problem, this is a momentum problem. You'll have to decide. So I'm giving you some clues here. When asked for acceleration, force is probably the first place to start. So I'm going to start with a free body diagram for the object on the ramp. I believe there's going to be two forces, force down the ramp and a normal force from the ramp. And I believe that's it. So normal force and weight. I need to align my ramp here, so do something like that. I want to try and align it with the ramp. So I'm trying to make the positive x direction down the ramp, and that makes the normal force aligned with the positive y direction. As said in your set of steps, the whole thing here is to try and make sure that one of your directions is the direction of the acceleration, and the other direction has to be whatever's perpendicular to that. So I'm going to recognize that I have one off-axis force. So I'm going to break it up into components. The 40 degrees is right here. So this will be one of my components, and this will be another component. And at this point, I would be strongly encouraging you to memorize the whole ramp arrangement. It's going to be the same every single time. There's no point in not having this memorized. It's always going to be the mg sine data pulling the object down the ramp, and it's always going to be mg cosine data that is perpendicular to the ramp. It'll be like that every single time. There's no reason why you shouldn't memorize it. It's going to make doing things like multiple choice questions go a lot faster. So I would just encourage you to. At this point, I apply Newton's laws. Net force in the x direction equals ma, and net force in the y direction equals 0. But a few people ask me why aren't they both ma? We're designing it so they're both not ma on purpose. We're purposely trying to make one of them 0. That's why you align one of the directions with the direction of the acceleration. So all of the acceleration's in that direction, and there's none in any other direction. You're doing that on purpose. That way this makes n minus mg cosine 40 equal to 0. And this one is just mg sine 40. That's the only thing that's acting in the x direction. They didn't give us the mass of the car, but you don't need it. Cancels out. So the acceleration is 10 times the sine of 40 degrees. Any question about where that came from? Initial velocity is 0. Displacement 2 meters. Find the final velocity. That's it. All right, Nate, that was number 5. Is that good for you? All right. We're pulling horizontally with just some force. We don't know what the force is, but we know that the coefficient of friction is 0.25. They use the word percentage, but we're more sophisticated now. We can use the word coefficient of friction. So that means that friction is going to be 0.25 of the normal force. They also tell me that this is a net force of 0 problem. Box moves at a constant velocity. Yeah, I should draw a free body diagram. But remember, a free body diagram is a construct to help us. I don't need that construct. You're pulling in to the right, friction had to be to the left, and they have to be equal. And net force in the y direction has to be 0 as well, so normal has to equal the weight. I mean, that's all you're going to draw, right, is 4 arrows for each of the forces. I just want you to remember that the whole point of the free body diagram is to help you conceptualize what's happening. And once you've reached a point where you can conceptualize it, drawing a free body diagram might be slowing you down. I'm not saying you shouldn't do it. I'm just saying that the whole point is for you to be able to create these. And if you know how to create those, you shouldn't have any trouble. And a free body diagram might just be more work. But I like to be thorough, so there's our free body diagram. And I'm lining it up X and Y. So either way, normal force equals 250. Friction equals 0.25 times the normal force. So my applied force has to be 0.25 times the normal force. That all good? I don't know, 4 divided by 25, or sorry, 250 divided by 4, 6 to 2.5. Right. We need that to be able to do the next problem. So any question about where any of that came from? All right. So now the problem is abridged to state that we're pulling at an angle. And we had to use the pulling force from before. 62.5 newtons. They tell us the angle? They must have. 25 degrees? Boy, I must have really liked the number 25 here. The box is still 25 kilograms. All right. They want to see what the acceleration of the system is. I think the assumption here is that by pulling upwards on the force, we have probably lessened the frictional force. And that might be enough for us now to have an unbalanced force and the system accelerates. We don't know that for sure. I want to be really clear. We don't know it accelerates for sure. So it's best to choose second law anyways. If you don't know if something's going to accelerate, you have to start with the Newton's second law and then prove there's an acceleration. So we don't know that it accelerates. The fact that they ask for an acceleration probably suggests it, but you still remember that you have to assume it's second law unless it's proven that it's first law. So again, drawing a free body diagram, this one has a little more value, I think. So I'm thinking we've got these 4 forces. So normal force, 62.5, friction, and weight. Any question about those choices? All right. I'm going to make this my horizontal direction. And I got positive X, and make this positive Y. I have one force that is off axis, so I need to find its components. So 62.5 times the cosine of 25 degrees and 62.5 times the sine of 25 degrees. Any questions about those choices? So I see people hurriedly write down. That suggests that maybe you can't do this one. This is way in the wheelhouse of what could be on your test. There's nothing new here. So if you're having difficulty with this one, you need more practice. I believe if it's going to accelerate, it's going to accelerate that way. That makes the most sense to me. So that's why I kind of chose the positive X direction to be in that direction, and that's where I'm going to say is my MA, and I still think the Y direction is going to be 0. I don't think I'm pulling hard enough to lift the box up. The box has a weight of 250 newtons. So the Y direction has 3 forces. There's the normal force upwards. There's 62.5 sine 25 also upwards. Minus 250 equals 0. Any questions about that? So looks like normal force equals 250 minus 62.5 sine 25. I assume this is going to be somewhere around 230. Is that right? What is it? Just so I can get it down. 223.6. All right, so that's the size of my normal force. I know I'm going to need the normal force later. It's a friction problem. And friction is always related to the normal force, so I'm going to have to get it. I have two forces acting in the x direction. I have 62.5 cosine 25 minus friction equals ma. And I know that friction equals 0.25 times the normal force. All right, this is what Newton's laws do for you. They give you relationships that maybe you can use to find something. In this case, I think we can find the acceleration. I think we have everything we need to find the acceleration. There's some substitution here for sure, but it still comes down to 62.5 cosine 25 minus 0.25 times 223.6 equals 225 times A. And I think that's enough for me. I think you guys can punch numbers. Any questions about that one? I'd say maybe a level 2 question, but it's pretty prescriptive. I mean, you follow your set of steps, it'll lead right to the answer. So by level of difficulty, I don't see this as particularly high. It didn't ask for anything weird. Let's just handle each part one at a time. So we'll start with accelerates upwards at 1 meter per second squared. So just so we have very clear, we're talking about an upwards acceleration, 1 meter per second squared. And I think the person has a mass of 50 kilograms. All right. Two forces act on the person. I think we've got gravity downwards, and that's going to be 500 newtons. And then there's a pulling force upwards that has to be, or a pushing force upwards. It's probably the normal force from the floor. And the normal force has to be greater than the weight because they accelerate upwards, so it's got to be unbalanced. On this next test, there should be care taken to making sure your arrows represent what's happening in your problem. So I am intentionally making sure that I'm drawing the normal force greater than the weight, exaggerated so. So there's no doubt that we all know the normal force upwards is greater than the weight downwards. So that will be a grading point on your next test. I'm going to make the up direction positive, so net force in the y direction equals ma. I want to point out something to you. If you're asked for the net force, you're just being asked for ma. There's every reason to think that that could be on your test. Net force is the sum of all the forces. So we actually know what the net force is. The person's mass is 50, the acceleration is 1. The net force looks to be 50 newtons. That's the net force on the person. But there are two forces acting on the person. There's normal force up, and there's weight downwards. If I want the normal force on the person, then that looks like 550 newtons. Any questions about that? All right. Part 2 of the problem. The elevator travels at a constant velocity. All right, well, I'm no longer accelerating upwards. That means my net force has to be equal to 0. That also suggests that these forces have to be balanced. So maybe something like that. The net force is 0. So normal has to equal 500. When the elevator first starts, you feel heavier. That's because the elevator is pulling upwards on you, and it makes you feel like you've been pushed downwards. You feel heavier. But it's just the upward force of the elevator on your feet. But when it's traveling at constant velocity, you probably don't even know it's moving. You don't have to know. I mean, you might feel a vibration or something like that, but at a constant velocity, you feel your actual weight. Without any visual cues in an elevator, it's hard to know it's moving at all. On the other hand, the last part says that it accelerates downwards at 2 meters per second squared. So this last one, the only way that can happen is if the normal force now is smaller than the weight. Right? Your weight doesn't change. What brings you to rest is gravity. Gravity's acting downwards on you. The elevator just pulls down less than it was before, so that the unbalanced force, the net force, is now 50 times -2. We have to make sure that we're obeying direction, and the acceleration was downwards. We've been making upwards positive the whole time. That makes the downwards acceleration negative. So the net force, -100 newtons. There's still just two forces acting on you, weight and normal force. So that's going to make the normal force 400 newtons. You feel a little bit lighter when the elevator comes to rest because it's pulling down less on you during the time that you're accelerating downwards. It only happens for probably a fraction of a second, the elevator coming to rest, but that's it. Those are your three parts of the problem. Now, I've given you the parameters of the question. If you want to make your capacity to pass the test better, every time you ask somebody around you a question, you should write down what question you asked and what the answer was, so that you have more information on how to proceed. So on any inclined plane problem, the plane is inclined relative to the horizontal unless otherwise specified. So we have a Hot Wheel car, it says, or something like that. So Hot Wheel car. There we go. And it's got mass M on a ramp angle theta. Okay? So this angle is made relative to the horizontal. So all of our measurements are made from there. There's no friction, I don't think, in this question, right? So it's just asking for the components of the weight down the ramp and the normal force. Did I get that right for the problem? Let me make sure. The first thing I will do is, if we ignore the friction, then your free body diagram has to look like this. And I want to promote something to you. The free body diagram is a construct. It's here to help you set up your problem. It is not the solution to your problem. And although you will be asked, I think, to make one on the AP exam, once you've gotten past some of the issues of setting these problems up, you're probably realizing that a lot of these problems end up being the same every single time. Be careful, because they don't have to be, but in many cases they are going to be the same every single time. Every single time I draw a free body diagram for a ramp, it's going to look a lot like this. And I'm almost always, unless there's some compelling reason not to, I'm almost always going to make the y direction aligned with the normal force and the x direction aligned with the ramp. That's going to dictate everything else about this problem. It's going to tell me that my angle goes here. And rightly so, because that represents this angle. It has to be there. And I can't choose to put it here just because it might be more convenient to me. Right? That's not theta. This is 90 minus theta. It's a different angle entirely. And no, you better not do your whole thing in terms of 90 minus theta. The AP graders don't like that at all. I'm going to make this the positive x direction. I think the car is going to accelerate in that direction. We had a mock quiz in first period that had one of these ramp things, and I still have plenty of people who don't know what to do here. But I can't make this any clearer. There is a component that has to be this direction, and then another component that has to be perpendicular to the first. these two have to be at a right angle. Has to be drawn this way. The moment I start seeing stuff like this, I know you have no idea what the components actually mean. That picture is an alarm to me. In many cases, to read yours closer, because you clearly have something screwed up. The components are lined up with the axes. So this is going to be mg sine theta, and it's going to point down the ramp. Every single time, there will be a component of the weight down the ramp that is mg sine theta. And every single time, there will be a component into the ramp that is mg cosine theta. You could memorize this. It will be this way every single time you have one of these problems. I would encourage you to memorize it. You don't have time to do all of this on a multiple choice question. And there's no reason not to have multiple choice questions about ramps since they are the same every single time. So subtext coming through here. Now, if we just stop at this point and not include friction, the net force in the x direction equals ma. It's accelerating down the ramp. And net force in the y direction equals 0. We designed it that way by choosing our x direction to be in the direction of the acceleration, which means mg sine theta equals ma. The acceleration is not based on the mass. I can cancel the mass out, and acceleration is g sine theta. This is if we don't have friction. The y direction, normal, equals mg cosine theta. That's not going to change whether there's friction or isn't friction. So now let's have friction as part of the problem. So now there is a coefficient of kinetic friction. That will change the problem by introducing a frictional force here. I don't know if this frictional force is greater than, less than the mg sine theta. I don't know whether the object is speeding up or slowing down. I don't have to know. I know the direction has to be up the ramp because the object is intending to slide down the ramp. That's what the problem said. Now that part is important. You have to know that friction is going to oppose the direction of the object. So if the object is traveling up the ramp, then friction's down the ramp. But if the object is sliding down the ramp, then friction is up the ramp, right? It has to oppose the direction of motion. I can't emphasize that enough. That does change what we have over here. And I said this at the very beginning, but I want to re-emphasize it. If you don't know if it's a first law problem, you have to assume it's a second law problem. I don't know if it's a first law problem. I have to assume it's a second law problem. That's going to be mg sine theta minus friction equals ma. But there's absolutely no reason to stop here. I should be able to do much more than this because I know that friction is equal to mu times the normal force, and I know what the normal force is. I'll still say that this is all that Newton's laws do for you. They construct a couple of relationships. And you were asked to find the size of the frictional force. So there's appears to be two different ways you could do that. You could find the size of the frictional force in terms of the acceleration. It would have to be mg sine theta minus ma. Right, this is the frictional force in terms of the acceleration. But also I could get the frictional force as mu k mg cosine theta. Correct? Now, when I go back to the problem, they didn't give us mu, so it makes more sense that this is probably my expression for the frictional force. All right. So I have a Hot Wheel car in a ramp, and the angle of the ramp is 40 degrees relative to the horizontal. And we're trying to figure out how fast the Hot Wheel car is going when it makes it to the bottom, which is 2 meters away. So, I mean, I hate to do it because we just did it, but I'm going to blow through a real quick free body diagram. So just more or less to prove it's the same every time. There we go. Normal force, weight. I'm going to do a a axis that is lined up with the normal force, like so, and like so. It says there's no friction, so these are the only two forces acting on the Hot Wheel car. That means that there will be a component of the weight this way and a component of the weight this way, and this has to be theta, or 40 degrees. All good? So the part of gravity acting down the ramp, mg sine 40, and part of gravity acting into the ramp, mg cosine 40. Any question about that? All right. So net force in the x direction equals ma, net force in the y direction equals 0. So mg sine 40 equals ma. I don't really need to worry about the y direction if there's no friction. So this is the only part that matters. And I can find that the acceleration equals g sine 40. The initial velocity is 0. Delta x is 2. I want to find the final velocity. I think that's about it. Choose a motion relationship and go with it. I'm thinking probably v squared minus v naught squared equals 2a delta x. So, box. The cables make an angle of 60 degrees with each other. So, does that look about right? So this is 60 degrees. And we want the least amount of tension in the cable to lift the boxes. Does everybody agree that the cables are symmetrical and therefore will have the same tension in them?
Yes.
All right. So I'm going to just save myself a little bit of time. I'm going to put my free body diagram right on top of this picture. And note that there's got to be weight acting downwards equal to 400 newtons, and that this angle is 30 degrees and this angle is 30 degrees. All good?
Yes.
I'm just going to do the components for one because they have to be the same for both. So there's got to be a tension upwards and a tension to the side. I'm taking just that one tension T and saying that this is T sine 30, and this other one here is T cosine 30. Does that make sense? So net force in the x direction equals 0, but this is going to be kind of silly because it's going to be T sine 30 minus T sine 30 equals 0. Doesn't tell me very much. But in the y direction, again, it's the least amount of tension to lift the box. That is a tension that provides net force of 0, and the box can move at a constant velocity. So I'm going to assume this is a 0 problem. It can be more than this, and the box accelerates upwards, but the least is it moving at constant velocity. So there will be a T cosine 30 plus a T cosine 30 minus 400 equals 0. So it seems to me that T cosine 30 equals 200, and T equals 200 divided by the cosine of 30 degrees. That's got to be the tension in the cable. Given on where, now again, if you have to do it this way, you're probably looking at a C on the next test. If you can do it this way, you're looking at probably an A or B on the next test. Everybody got it? Or worse. I mean, I say C like curved, okay? You're going to have to be able to do this or you're going to lose points. So the box is going up the ramp. I'd like to know how far till it stops. What's delta x? Where does the box stop on the ramp? It may stop and slide back down, but where does it come to rest? So let's start from this free body diagram. Move that over there. I'm going to put a coordinate system in. Nope. Let's use red. We always use red. So I've lined up my coordinate system with the ramp. And that means my other one's going to be lined up with the normal force. What do you want? Do you want to the left to be positive or negative? Negative. All right. David was the first one to speak up, so that means up the ramp is positive. All right. Up, positive. I see a component this way and a component this way. This one's mg sine theta. This one's mg cosine theta. Again, same as every other time we've had a ramp question. Net force in the x direction equals ma. Net force in the y direction equals 0. We set up our coordinates in order to make that true. That means normal equals mg cosine theta. And that means minus friction minus mg sine theta equals ma. Any questions about these choices? All right. I have one more thing I can do. I know that friction is equal to mu times the normal force. All right, force concept model gets you to here. What you do next, this is algebra. Right? So let's do the algebra. I know that friction must equal mu mg cosine theta. That's kind of a given at this point. We do this like every time. Like I said, there's a lot of repetition here. So I'll have negative mu mg cosine theta minus mg sine theta equals ma. I know that we have numbers. I'm purposely doing it without the numbers, because if you can do it without the numbers, you can do it with the numbers. I am noticing that there is an m in both terms on the left. I'm only doing this step because I have some folks who are really struggling with algebra. I can factor out the m from both of those terms. That means I can multiply both sides by 1 over m and cancel out the m's. Now you have all the numbers here to get the acceleration. And the acceleration works out to be negative because it points down the ramp. Once you have that, final velocity is 0, initial velocity is positive 3, find delta x. I'm pretty sure this comes out to be like 5 point something meters per second squared.